Okay, hello. Welcome to Scrap Paper and Philosophy. And I would like to thank Paul for watching. Really, I appreciate it. And one reason is that I know you're a skeptic. If I'm not mistaken, your father was a physics professor. So, if I can convince you that modern physics made a mistake and a big one, I can convince, probably a whole lot of people. So, before I even get into what the mistake is, last time we were talking about, last time we ended up with this right there, right? E equals mv squared. And the way we came up with this is replacing force by energy over distance. An energy expenditure over a distance representing a force on a mass equals the mass times the velocity squared. And so before we even get into what the mistake is, I guess I should just briefly mention this, right? And what this is let's go back to what we were doing last time. There was, there was the four elements. They were, no, I wasn't going to say that. They were the four elements: distance, which by the way is always a positive number; time, another number that is always positive; energy, no negative energy, energy, always positive. And then, what's the fourth one? Time, distance, energy, and mass. Definitely positive, right? I mean, what is antimatter really? And we'll discuss that later. So we have distance, time, energy, and mass. And the reason why we're calling these the four elements is that they are the ones that can more readily be related by force equals mass times acceleration. There's many different tricks we can play here if we're relating distance, time, energy, and mass. One of the tricks we can play is solve for time. And here's time. No. Wow, almost knocked the cell phone down, but we're recording. Okay. So I'm so excited. Okay, so here's time, right? It's distance divided by the square root of mass over energy. And I'm sorry about not being consistent. I mean, I was using capital E for energy as elsewhere, and now I'm using lowercase for energy. But that's what the point is. I mean, the point is that there's only four quantities, right? Time, distance, mass, and energy. And if we solve for time, this is what we get. And the remarkable thing about this, I mean, other than trying to understand it, which we don't, but even without understanding it, what it means, the remarkable thing about it is that the period of a pendulum, the formula, if you look up on the internet, the formula for period of the pendulum, this is what you get. You get 2 pi times the square root of the length of the pendulum over little g, which, as we all know, is 9.8 meters per second, but it could be something else. So there's the formula. And even if the terms don't correspond to mass and energy, the length of the pendulum and the acceleration due to gravity, we see that the same operation is being computed. I mean, the computation is, we're taking a number and we're multiplying by the square root of a ratio. And is that a coincidence? Well, um, I don't know. This is something I haven't really thought about, but here's something that I have thought about, right? And which is the similarity of E equals mv squared with E equals mc squared. And here, I'm going to say that this is not a coincidence, that they are actually identical. And the implication here is that electromagnetic waves are stationary. So that's that's something that we aren't really familiar with thinking, because we're taught that electromagnetic waves are not stationary, right? They are traveling at around 3.0 times 10 to the 8th meters per second. But then there was a formal definition made. They adjusted the meter. I mean, I think it all works out so that the force between two wires carrying 1 coulomb of charge should be 1 Newton if they are separated 1 meter apart, and that's the definition of a meter, and they somehow got that to relate to the speed of light, which used to be around 3.0 times 10 to the 8 meters per second, as measured by the Michelson-Morley experiment and other experiments. But now it was subtracted a little bit, so it's like 2.99. I don't know, 2.97. I don't know. I don't remember what it was, but times 10 to the 8th meters per second, or as I'm used to thinking of, around 300,000 kilometers per second. That's how I was used to thinking about it, but not anymore. And if we're right, this is going to have some applications to signal space, because we're going to be able to locate electromagnetic structures, and that's going to let us say things about things like cryptocurrency. I mean, we could come up with the idea that we could like understand a cryptocurrency as an electromagnetic structure, and then we can make assessments about whether we want to use cryptocurrencies or not, because we can say things like, oh, the electromagnetic structure that your cryptocurrency is leaving is really ugly. I don't like it. And there's holes, right? Maybe we can point to holes, who knows, in the electromagnetic structure. So that's going to have applications, very sophisticated applications to signal space. But we're not there yet. What we want to do is applications to physics theory. And we're going to motivate this by discussing the law of... by discussing the two postulates of special relativity, and we're going to derive the law of conservation of momentum, right? The conservation of mass is going to be pretty obvious, right? We're just going to take that kind of like as a given, and then from that we're going to go to the conservation of momentum. And one thing that I really suggest you look into is Noether's theorem, Emmy Noether, right? She understands conservation laws as symmetries, and so that's a good place if you want to review that. And we're going to lack experimental proof for now, but we'll get into that later. So I already have some idea about how we can look for experimental proof, so we'll have to discuss that too. But today I just want to contemplate, well, with you, the similarity between these two formulas. And of course, this is what Einstein's giving us. And what I interpret this to mean is that if we had a mass and we were to convert it completely to energy, right? For example, a matter-antimatter collision, the matter is completely annihilated and transformed into energy, and we want to find out how much energy we got from that transformation, right? We got mc squared. Now, this is what we got last time. And what we are going to say is that these are actually identical, right? So matter is traveling at the speed of light. This is this e squared. This e squared equals to this v squared, right? This m equals to this m. This e equals to this e. And so before we go any further, let's just have a kind of sanity check. Let's see. We have force equals to mass times acceleration, right? What is that formula really relating? It's very referential to this mass here. It's saying that if we apply a force, I'm just gonna put the pen right there because that's what we're really looking at. Right? We're looking at the mass. If we apply a force to that mass is going to accelerate. So from that, we were able to derive this. And again, we see that it's completely self-referential on mass. If a mass is traveling at a particular speed, we take the square of that speed, we get the energy of that mass. And the question is, what is the speed? Well, mass is traveling at the speed of light, and light is stationary. And of course, we'll have a lot more to say about this. And again, I'm trying to keep these videos short, so see you next time. Take care.